Now let us do a small mathematical analysis for the natural sampling. What we have drawn right now are the waveforms in time domain. Let us see what are their corresponding frequency spectrum. So the very first signal is my modulating signal. I can call the modulating signal as m of t. The second signal is sampling signal. Let me call the sampling signal as s of t. And my output signal, I'm going to call it MST, where MS is the sampled version of the signal. So you can see that I can simply obtain MST by multiplying modulating signal with the sampling signal. So when you multiply, the value between the two rectangular pulses is 0. 0 multiplied with m of t will give you 0. And every rectangular pulse, when you multiply with m of t, its amplitude will be exactly same as amplitude of m of t. So simply the multiplication will give you the sampled version of signal. This is also what we had taken in case of the ideal sampling. So the very first equation I can write is the sampled version of the signal is product of m of t and the train of rectangular pulses. However, s of t, which is a periodic signal with period ts, can be expressed using its Fourier series representation. So using Fourier series, we can write s of t. The Fourier series of s of t, which we generally find in signals and system, will be given as a tau upon ts, where a is the maximum amplitude of the rectangular pulses, tau is the width of every pulse, ts is the time period, summation sync is one very important function, n tau by ts multiplied by e raised to j 2 pi n t upon ts. So that's the expression of the Fourier series. The summation variable n will go from minus infinity to plus infinity. So my sample version of the signal then becomes m of t, which is my original signal, will be multiplied by this whole thing. What I'll do is I'll take m of t inside the summation. So a tau upon ts summation sync of n tau by ts into e raised to j 2 pi n t upon ts multiplied by m of t. That original m of t is multiplied. Please remember, summation is with respect to n, and hence m of t can be written inside the summation also. You guys will have to refer signals and system part of Fourier series specifically and understand how this Fourier series of rectangular pulses is derived. You can remember this expression for this mathematical analysis. The next part will be, now this is the expression in time domain where we have replaced the sampling signal using its Fourier series expression. Now let us take the Fourier transform. So if I take Fourier transform on both the sides, taking Fourier transform, we will get frequency spectrum of sampled version of the signal. On the right hand side, when I take the Fourier transform, summation and Fourier transform are linear, and hence I can go inside the summation. Summation will remain as it is. Sync function do not have t time variable anywhere, so it will be treated as constant when you apply Fourier transform operator. It will only operate upon the part which depends upon time t, and which is this exponential term multiplied with m of t. The Fourier transform of m of t is, let's say, m of f. What will be the Fourier transform of m of t when it is multiplied by a complex exponential function? We use a property of Fourier transform which is called frequency shift property. If Fourier transform of m of t is m of f, then the Fourier transform of this whole thing will be m of f minus n by ts, because n by ts is that parameter by which the frequency will be shifted. N will vary from minus infinity to plus infinity. And I can further write this expression as a tau upon ts summation sync n tau upon ts into m of f minus n fs, because 1 upon ts is fs. N will vary from minus infinity to plus infinity.